Welcome to Always Remote, using M2 for research and teaching. In this session, we'll be covering essentially how to use M2 for research and teaching. M2 is our high performance cluster. We'll explain a lot more about what that means. And it's great for students, great for researchers, and we'll be giving you kind of an introduction for how to use it, how to access the M2 portal, along with a little tutorial, assuming we get time to actually get all the way to that. You don't need to know how to program. We're going to try to keep this within the 45-minute time limit. All of your microphones will be muted. If you have questions, post them in the chat, and we'll kind of answer them as they come up. So if there are a ton of questions, then we might end up having to cut the tutorial a little bit short, but we're going to try to get through everything by the end. If we don't get to your question, somebody will follow up with you after the session. So with that, I'm going to hand it over to Rob, and we'll go ahead and get started.
All right. Good afternoon, everyone. Let's see if I can get off this first slide. There we go. Okay, so first I want to introduce myself and Eric, who will be walking through everything today. We're part of the OIT Research and Data Sciences Services group, and also the Center for Research Computing. So the Research and Data Sciences Services group provides, obviously, research computing support. And this is basically broken down into three major parts, right? So where we have data science type support, which is done by Eric, and high performance computing, which is done by myself, and Internet of Things and wearables and kind of custom devices and data acquisition by Guillermo. We cross paths a lot. There's a lot of projects that we all work on where it's not just one of these buckets, but we kind of work together on various things in a lot of ways. Mostly what we'll be talking about today is ManeFrame II and its applications around campus. And so that would be for high performance computing. The Center for Research Computing is kind of the faculty governance body for HPC on campus, and namely right now that is done with ManeFrame II, and this is done in collaboration with OIT. The center provides research computing tools and support and training for faculty and staff and students using HPC in their research and for teaching. So essentially everything that I'm going to and we're going to discuss for the remainder of the presentation, you can find at ManeFrame II's documentation site, which you can get to from smu.edu/crc. And if you have any questions after, feel free to reach out to either of us. I should say that all faculty can get an account on M2. And all you need to do is request one, and there's a link at smu.edu/crc to get one. So I always like to start out with a little bit of Hpc Back History for SMU. SMU has actually been in the advanced computing business for quite a long time. Back in the mid-50s, they built the UNIVAC Computing Center. And it was designed specifically to house the UNIVAC 120, which is, let's see if you can back here. This machine is a vacuum tube machine, famous for its time in the limelight in the mid-50s. Right? This printer that you can see on the left could do about a line per minute of printing. So imagine trying to print out a dissertation on that kind of machine. So, and it used punch cards. Most people probably here today are familiar with punch cards, but I get a lot of students who are not familiar with what a punch card is. So we've come a long way since then. Okay, so let's talk about the state-of-the-art machine, ManeFrame II. ManeFrame II features state-of-the-art CPUs, accelerators, networking technologies, a substantial amount of memory per node, and I'll discuss what a node is here in a minute, and advanced interactive GPU accelerated remote desktop experiences, right? So all of these things are of note in that they were a large step forward over ManeFrame I, and M2 has been expanded upon over its life to continue to serve the research needs of faculty and research groups across campus. Right. M2 runs Linux. The specific type of Linux that it runs is called CentOS 7. Now, I'll mention that while it does use Linux, the Hpc Portal, which we'll discuss a little bit later in the presentation, and hopefully have a demo at the end, allows you to sidestep a lot of the Linux-ness of the system. So if using the command line, if you hear Linux or Unix or that like, and you are not familiar with doing things at the command line, you need not worry. We have a great way to get to use the system without actually having to do that. You can jump right into a lot of familiar tools, which we'll discuss. Okay, so M2 is a shared resource, and so we use a system called Slurm, which basically schedules who gets what access to specific parts of the machine at any given time. We use the LMOD environment module system to basically manage access to specific pieces of software on the system. I like to point out these three pieces, CentOS, Slurm, and LMOD together, because if you are doing research in the future at another institution, it is very likely that they will use these same three together. And so I point that out to say that a lot of what I'm going to be talking about and we'll be discussing today is specific to M2, but a lot of the tools will abstract nicely to a lot of other machines around the country, right? So it is good information to use elsewhere if you are collaborating with someone else in the future outside of M2. We have lots of development tool chains you can use to build code or write in Python, what have you. So if you're doing C or C++ or Fortran, we have lots of compilers to choose from and lots of highly optimized math libraries to build upon. And we also have lots of optimized high-level programming environments such as MATLAB, Python, and R, with many different versions of each. And different packages associated with them that can be tailored to the specific workflows and needs and requirements for your specific research and teaching. Okay, so ManeFrame II is what we call a cluster supercomputer, and a cluster is just a collection of individual nodes or machines. So I will use the term node a lot, and all that is a computer in its own right. So it's, M2 is really just a collection of many computers that are all networked together. Each computer that comprises M2 is very powerful in its own right. And the networking that connects them is very fast. It's high bandwidth and low latency, which is the kind of network that you want when you want the individual nodes or individual computers to be able to talk to each other as quickly as possible. Within each node, most of the nodes on M2 have multiple CPUs, have 2 or 4, and they all have lots of cores, right? And so the goal of HPC in general is to use as much of this computing resource as efficiently as you can to solve whatever problem that you are trying to tackle, right? And so there's this inherent parallelism that needs to be applied to the problem that you're trying to solve. Right? And I will say that is my bread and butter. So if you are not sure how to divide up that problem, such that it can be done in parallel, I'm happy to discuss that with you. M2 is also a heterogeneous cluster in that it has many different node types. And these different node types are to serve different kind of use cases of the machine, right? And to go through this list, you'll see that the biggest differences are the number of different types of nodes that we have, the number of cores that are there, and the amount of memory associated with the machine. And then some of them have advanced accelerator cards attached to them. The big point that I want to convey here is that each of these node types has many more cores and much more memory than you're likely to find in any machine that you would have sitting around your office or in a server closet down the hall or the like, right? So most of our nodes have 36 cores, so it's 2 CPUs, each with 18 cores. So your average laptop or desktop machine is going to have maybe 4 or 6 or the like. And the amount of memory, the least amount of memory that we have on any machine is 256 gigs of memory. Compare that again to what you would likely to find on your average desktop or laptop is, 18 or 8 gigs or 16 gigs, maybe 32 if it's very high end. So we are, our base node type has much more than that. Okay? And so why is this important? This is important because if you want to parallelize your code to have it run in multiprocessing or through threading, or you have a large data set that needs to fit into memory, you need the cores and you need the memory to be able to handle that, right? And so a lot of the top half of this list with the standard memory, the medium memory, and the high memory are just different configurations of core counts and memory, topping out at 1.5 terabytes of memory. Then the bottom half of the list is primarily nodes that have accelerator cards, right? And so the rest of the node itself is very similar to what we just discussed, but in addition, they have a GPU associated with them. And the term GPU stands for graphical processing unit, which is a little bit of a misnomer because these GPUs are not really used for graphics at all, but rather just computations. They are very good, particularly at linear algebra type operations as applied to many, many domains across research and teaching, right? And certainly if you're doing any sort of machine learning or AI, where you're training a data set or applying a model that has been trained using a data set, GPUs are where that happens most efficiently, for sure. And then we have a number of faculty partner nodes, and these are nodes that are purchased either by faculty or in collaboration with SMU for specific research needs. And as part of that arrangement, they get added to M2. I will say that these are available for people to use when those research groups aren't using it. The system is backed up by several storage systems, the largest of which is called Scratch, and this is a nearly 3 petabyte file system. So a petabyte is 1,024 terabytes. So it's nearly, we're looking at about 3,000 terabytes of usable space. Okay, so when you first log on to the system, you are in your home directory. And your home directory is an NFS-backed file system located at /users/your username. For those that are unfamiliar with kind of Unix command line and scripting and the like, the $sign indicates a variable. So $, all caps user is just your username on the system. So in this case, it'd be R. Koleski for me, and $home, all caps, just points to your home space, right, on the system. This file system should be treated as kind of your space to keep things that are what we call irreplaceable, right? So code, important results, things of that nature, right? It is backed up off-site, but is restricted by quotas. You have 200 gigs of space here. I generally tell people that you should think of this space as small and slow, right? Meaning that when you are running calculations, you don't want to run from this storage space because it's not designed to be fast. It's designed to be redundant and backed up. Right? A new storage system that we just added called work is $work and is located at /work/user/your username. This is a much larger space. It is faster. Each user has up to 8 terabytes of storage on this space, and it is intended for long-term storage of data. Right? So if you have a data set or kind of intermediate results from computations, this is where you should store these long-term. There are no time limits for how long the data can sit on either work or your home space. And then lastly, there's the Scratch space, right? And this is the nearly 3 petabyte file system that I mentioned earlier. This is located at /scratch/user/your username. And this is a high performance parallel Lustre file system. It is designed to be very fast. It handles larger files better than it handles a lot of very small files. But most kind of big scale computations that are done on M2 are looking at kind of large data sets with large files. And so this file system is tuned for that need. If you are working with a data set that has lots of small files and you're doing lots of small read writes to those files, which is sometimes the case, there's nothing wrong with that. We have actually a 4th file system that I'd be happy to discuss with you. But that is kind of because it's small, you need to be authorized to use it. That said, you should treat Scratch as a volatile file system, right? Which means that it may go away at any time, right? That said, many people use it for kind of long-term storage, and we're trying to, with the new work file system, move that kind of workload onto the workspace and use Scratch for what it truly should be, which is a Scratch space, right? That said, Scratch is quite redundant, and so we don't really have issues with data loss. M2 is located in the University Data Center, which is located off of Central, just south of Mockingbird. And so it's designed as a lights out facility. No one has a permanent office there, but people are working there all the time. So this is what the machine actually looks like. It's a collection of individual computers or nodes, as I had mentioned. And so you can see here on the stand on the left, the individual nodes. So there's a stack of 4 sitting there. And they're about the size of a large pizza box, and they slide into the rack and are connected in the back for power and networking and the like. And so you end up with just cabinets stacked one on top of the other for all of the individual machines comprising the cluster. M2 does what is called hot IO containment. So all these machines, as you would expect, generate a lot of heat. And so it comes up through the floor, through the grating. It gets pulled in by the fans of the machines into a center aisle, and then it's exhausted out the ceiling in the center aisle, and where it's recooled, and that process happens continuously. And you can see that all the networking and power is nicely done, all up in the rafters above. There are some large AC units on the roof to cool all of that. And there's also a gas-powered generator. So it is not uncommon, it's not terribly common, but it does happen where during thunderstorms, your power might go out at your house, or Power might go out even at SMU. And you can rest assured that your calculations on M2 are continuing to run during that time. I like to tell users, because sometimes I get emails about it in the middle of a thunderstorm, that your connection to M2 may be severed due to communications going down, but the computations that we're running on M2 and we're scheduled to run should be proceeding. Okay, so how do I access M2? There's two major ways to do it today. There's SSH, which stands for Secure Shell, and this is the kind of classic terminal-based, opening a terminal window on whichever operating system you're using, and you can use your credentials to log in, your username and SMU password to log in. SSH allows what's called X11 forwarding, which allows you to run graphical applications off of M2, and they will be displayed locally on your own machine. All major operating systems, so if you're using Windows PC or a Mac or a Linux machine, they all support these features through either natively, if you're using Linux, or with several additional software packages if you're using Windows. The details of those can be found on the documentation site for M2. The other way to access the machine is the Hpc on-demand portal. And this provides a completely web-based access to all of M2. It includes a web-based terminal. So if you just want to hop on to look at something real quick, there's a terminal there, which is nice. And it gives you web-based access to Jupyter Lab for Jupyter Notebooks, if you're using that with Python or R or Julia or some of the many other languages that Jupyter supports. If you are using RStudio, you can run RStudio directly off of ManeFrame II via your web browser. And it also supports remote desktop. So you can launch a Linux remote desktop instance off of one of the nodes of M2, and it shows up right there in your web browser. Transferring files is quite easy. This is a very common question that I get. How do I get data to M2 and how do I get data off of M2? And an SFTP client is how that is done. So you can do it from the web. The Hpc Portal also has a file browser of sorts. And so you can access your files through the portal there, or you can upload and download files off of M2 that way. Most people using a Mac or a PC will use one of those two options there, CyberDuck or Transmit for macOS, or WinSCP or CyberDuck for Windows. And I should say that if you're using any sort of Unix-like environment, either on a Mac or a Linux machine, or something like Cygwin or WSL on a Windows machine, there are many, many command line tools that you can use to transfer files to and from M2. The unifying feature of all of these is that they need to support the SFTP protocol, which is not to be confused with FTP/S, which is a completely different protocol. So kind of giving a quick example of how this works with WinSCP, most of these tools basically provide you with two panes, where on one side you have your local files and on the other side you have your remote files on M2, and you can simply just drag files back and forth. And this works great for most kind of workflows that people are doing for moving data back and forth. One thing is that if you are finding yourself moving terabytes of data back and forth frequently, definitely reach out to me. We have other methods for moving that amount of data around that are better suited. Again, not a terribly uncommon use case. So it's good to have options. The Hpc portal, as I just mentioned before, as a way to access, can be found at hpc.smu.edu. You log in using your SMU ID and your SMU password, and it goes through the normal like Duo authentication and whatnot. And then you're provided with the options for how you would like to interact with the system. Okay, so I'm going to go quickly through kind of the uses of Slurm and the module system for how you would access software, and then we'll follow that up with the demonstration of the portal. If you are interested in learning a bit more about using the command line on a Linux system or a Mac or Windows WSL, we have a nice Unix tutorial, which can be found at that link. And I also have a cheat sheet, which is just a PDF that you can print out that basically summarizes all the tables that we're going to be looking at, in addition to kind of basic Unix commands. I found that people like to sometimes, especially new users of M2, will print this out and have it nearby for while they're getting up and running on M2. Okay. So the first thing when you're using M2 is you're going to want to access applications and tools. We have lots of software available. This is what I'm showing here is kind of how it's structured, but we have many thousands of applications and libraries and different versions of each that are available depending upon your research needs. The way you access these applications and libraries is through the module command. And there's only a few kind of verbs that go along with this command. It's actually quite a simple tool. Module avail will pull up the packages that are available, similar to the screen that I just showed. And if you want to load a package, you just do module load, such as module load Python will load the default version of Python on the system. Module list will show the modules you currently have loaded, and then you can unload a package that you have loaded. And the reason that this is useful is, for example, Python, right? There are many different versions of Python. A lot of people started out using Python 2.7 as the version that they are, building against. And mostly people have migrated to various versions of Python 3, but that's certainly not 100%. So we support both, and you can load whichever one is convenient for you at the time. Same with different versions of GCC. We have, I think we're at least 6 different versions of GCC on the system, tailoring to different people's specific needs for packages. And so this allows you to pick and choose exactly the software that you want for the workflow that you're doing. Module purge is my unabashedly favorite command. This unloads everything, right? So I like to make sure that I'm always starting with a clean slate. And so I might have loaded a whole bunch of things and I just want to start over or unload everything so that I can build up a new set. Module purge is how you do that. And so I encourage lots of folks to use it, and I'll actually demonstrate its use in just a moment. If you want to search for packages that have something specific to do with Python or some other keyword, you can use the spider command. It's basically a module search tool. And if you have a set of modules that you would like to use all the time, that you set up very carefully, you can save that as a name set so that when you first log in, it'll just do that for you, which some people like, or you might have like version 1 and version 2, version 3, that sort of thing. You can do that as well. We have a tutorial walkthrough that shows you kind of how to do this at the documentation site. Okay, so submitting jobs using Slurm on M2. So as I mentioned kind of early on, M2 is a shared resource. There are many people using it at any given time, submitting many jobs, and those need to be balanced across the system. And we use Slurm to do that balancing for us. The first question that you have to ask when submitting a job to the system is what kind of job am I submitting, right? So serial what I call shared memory or distributed memory. So serial means that it's doing nothing in parallel. It's just running a script, or you have one calculation that's just going straight through, and it's not doing any sort of parallelism, threading, multiprocessing, nothing like that. That would be one class. Shared memory are things that can do things in parallel, but are staying on a single node. And distributed memory means that they are using multiple nodes together as one. So for serial, it's very common for serial calculations to be done kind of en masse, right? So you'll submit one script that can launch, 1,000 separate tasks. And usually this is to get statistics over many trials, or you're doing kind of a parameter sweep is common to see in this case. Shared memory tend to be more computationally demanding packages that have built-in threading, and distributed memory are most demanding, where they're using MPI to communicate between the nodes. So how are these resources managed? We use a queue system, right? So you submit a job to Slurm, and it will decide when and where that job should be run. There are lots of queue systems around. They work largely in a similar fashion. Slurm has thankfully become kind of, not quite the de facto standard, but it's very popular among HPC systems. M2 is governed by what we call the fair share factor, which is simply that preference is given to those who have submitted the fewest number of jobs. And essentially the reason for this is it prevents blocking. So if I have a set of computations that I want to do where I'm going to submit 1 million serial jobs, I don't want everybody on the system to have to wait for all 1 million of my jobs to finish, right? And so basically what it allows for is additional jobs to show up in the queue and basically skip the line, right? And they get to get pushed in front of other jobs. And it's the fair share factor that governs that. All jobs are basically put through this process of deciding where they should run at any given time. And it's a complex algorithm of basically how many jobs have you submitted and how long have they run and how long do they think it'll run and things like that. So, we have lots of queues that you can, or partitions to stand in. And so think of these as lines that you can stand in for different types of resources. The two biggest delineations for the queues are the type of physical resource. So is it a standard memory node, or is it a medium memory node, or a high memory node? Does it have a GPU, et cetera? And how long do you think your computation is going to run, right? And for most of them, we have on the order of what we call short, medium, or long, which is 1 day, 1 week, or 1 month. And then for some of the other kind of specialty nodes, we have 1 week or 2 weeks, depending on how the specific node type. So a common question that I get here is, are these hard limits? Yes, they are hard limits. I like to say that if you did a standard MEMS job and it ran for 1 day and 5 minutes, it didn't finish. Because Slurm will kill it at 5 minutes. So you have to have an understanding of how long your job is going to run for. That said, the second question that I get a lot is, how do I know how long my job will run on the system? And the best way to do that is to experiment. Start with a small data set or a subset of what you need to do and see how long it takes, and then build up from there with a larger data set or a more exacting method or something of that nature, right? Again, if you're not sure about how to go about doing this, absolutely reach out to me, and it's something that we can discuss. Slurm basic commands essentially are how to submit a job and view jobs that are running, right? So SQ-U and your username. Remember, the $user stands for your username on the system. will show you your jobs that are currently queued or running on the system. There are two major types of jobs that you can submit, either what we call a batch job or an interactive run job, S-run job, right? Interactive means that you want to have it done right now, and you want to interact with it. Like, for example, if you wanted to run the MATLAB GUI off of M2, that would be something that you would want to run right now. A batch job is something that you submit with a batch script, and it will run at some time in the future, maybe the middle of the night or whatnot. And then you can also cancel jobs. So an example of a batch script is this. The top there basically tells Slurm what kind of job you're running. Gives, you can name the job, what partition do I want to stand in or which queue, how long do I think it's going to run. There are lots of other flags that you can put there. How many nodes do I want? How many cores do I want? How much memory do I need? Things of that nature. Again, if you are uncertain about how this would apply to your specific workflow, please reach out to me. And there's my favorite module command, module purge. I always start all of my SBAT scripts with that to make sure that we're starting with a clean slate. And this is just to show that you can get quite complicated in these scripts and do complex workflows, make directories, copy files around. So you can get quite creative with how your workflow can be done through the queue system. And we have a Slurm tutorial, which will walk you through some of the features of using the system. Eric, do you want to?
Yeah. So as Rob said, if you have any questions or you need help, feel free to let us know. And with that, I'm going to start sharing. If I can find the button. Should do it. Can everybody see that? Okay. So first, I just wanted to kind of show everybody. So this is the Center for Research Computing website. It's at smu.edu/provo/crc. And a lot of information that we've talked about can be found on this website, from the statistics on M2 to some documentation, our workshop schedule. This is still fall 2020, but it'll be updated for the spring, as well as requesting an account. So if you don't already have an account and you're faculty and staff, all you need to do is click this form. You go through and fill out the information, and an automated request will be sent to our HPC admins, who will then make you an account. If you are a student or a postdoc, which I know none of you are, but you might have students or postdocs, they will need a sponsor, which is generally the faculty member they're working with or whose class they're taking. And they can fill out the form themselves, and there's some branching logic in there so that they get the appropriate information from them. So with that, if we go to hpc.smu.edu, and I've already signed in, you can see I'm logged in under my credentials. This is our web portal. It's called an on-demand portal for HPC. And you'll see here's our workshop schedule again. And this is kind of our home landing page. So if we were to log in via a terminal, we would get something that looks like this, which anyone who's never used Linux might be cringing right now, thinking back to some old text-based video game from their past or something where they probably died of dysentery. But you don't have to use the system like this. You totally can. I did an entire PhD using the system exclusively like this. I know Rob and I find this probably more comforting than anything else. But there are other options. So this is, you can get to a terminal just by going through clusters again and then shell access. But you can do that also if you have a Linux machine, a Windows machine, or a Mac. and just have a terminal app on your actual computer, and you can log in via SSH, like Rob mentioned. Where the portal becomes, I would say, explicitly valuable is this kind of interactive sessions button here. And so from here, and I already have some running, so that kind of the at-home cooking show approach. But let's say I wanted to work on Jupyter Lab. I can click here, and I can specify my own environment, and I can do some kind of custom settings here. And if you have questions on any of this, we have tutorials and a lot of information for how to do this, which partition to choose, how many nodes, how many cores, all of this stuff. And I can click launch, and it'll bring up a window that looks kind of like this. And I can hit connect to Jupyter Lab, and it gives me something that looks like this, which is Jupyter Lab running on the M2 cluster. So you can see here all of my files and all of my various scripts and everything that I've written. And I can do Python, MATLAB, R. I can even do a terminal if I wanted to. You know, I can do the full terminal commands like I normally would. I can upload files. I can write my own text files. There are even widgets and all sorts of other things you can do here. And you can just open Python in a notebook and immediately start programming. And so here I have some demo code that shows doctorates issued by SMU, for instance. Okay, but maybe you don't use Jupyter, maybe you're more comfortable with, say, RStudio. So we can go back to our interactive session. We could click on the RStudio server button. And again, it'll open a window that looks like this. It'll say when it's created, when it's running. And we have a full functioning R instance, you know, R version running version 3.6.2. If you want a different version, you can do that as well. And again, we have the file viewer, just like RStudio you would have on your own personal machine, you know, with a terminal access and everything. So, but maybe you're trying to do something that needs a graphical interface, and you don't want to use the terminal, but you still need it to run on M2. So you can actually open a virtual desktop. So this is, let me move these out of the way, a full Linux desktop running off your M2 file system. So you can see here are my files, looking just like it would if you had your computer was a CentOS 7 machine. That being said, it is a little kind of bare bones looking. Scientific Linux and CentOS 7 are pretty bare bones looking systems. So it looks a little bit kind of like Windows 96, but stripped down for efficiency, you might say. And with that, you can actually launch a terminal inside of your virtual desktop. And so this is kind of just an example. VMD is a software that does visualization for molecules. And here we have kind of a 3D graphic spinning around, running on our M2 system. We also get questions about SAS. And so I can run SAS, which again has lots of clickable buttons and things that you normally wouldn't want to run in a terminal. And you can run SAS inside this virtual desktop environment, again, utilizing the M2 system as well. So this is like remoting into the most powerful SAS computer you can get your hands on, which is, from what I understand, way better than trying to install and use SAS on your personal machine. So that was quite a run through. I know that was the end of our session. But I think we have just a couple minutes if we have any questions. So I guess we have 4 minutes. So if anybody wants to chime in, Rob and I are happy to answer questions. If there's something that we can't get to, again, we'll reach out afterwards and let you know. So. Does anybody have any questions? Thank you, Carlos. Glad it helped. Well, thank you for attending the session. The session's been recorded, as I'm sure you all noticed. It'll be available on the same site that you registered for it. I think they'll get posted by early next week. And again, if you want access to the slides won't exactly be posted with the recordings. But if there's something you want out of the slides, just send us an email at egodat@SMU or rkoleski@SMU, both of which are in the chat. And we're happy to talk to you and send you the slides.
Yeah, or you can go to the M2 documentation page, which actually has an expanded version of that slide deck. So you can get exactly those slides plus about 60 more.
So if you're a glutton for punishment, you can go back and get
yes,
get Rob's expanded version. Or if you really are interested in this stuff, make sure you come by. Rob does a lot of HPC workshops. We do a little bit of data science workshops sprinkled in with that as part of the Center for Research Computing and the data science services team. So, well, thank you all and have a great day.